Hey guys, welcome to the third installment of the rates of change topic. So in the last few videos, we basically covered the principles for deriving rates. So whereby whenever you're trying to find a rate of change of a particular variable, it's d, whatever variable that is, over dt, right? dt is the thing that represents rates of change in the advanced and extension 1 topic. Last lesson, we then applied those principles in the first video to a few past paper questions, where the last one was quite interesting because it had a Pythagoras application on a right angle triangle. And I sort of alluded to the fact that there is a more sort of, some people consider it harder, but it's much more efficient method called implicit differentiation. Now, some schools only do this for extension 1 classes. There's no reason why advanced students can't apply it as well. It's not actually that hard. In fact, once you see it and you know it, it's a much faster way of doing it. I guess before we begin, right, I'd like to maybe give you a bit of theory just to really touch on, once again, what rates is all about, and also what the implicit differentiation topic, so method looks like. So maybe I'll give it a title, Implicit Differentiation. So some schools don't actually teach this method, which is kind of like a bit of an oversight, because there's a lot of questions, right? There's a lot of questions, and it's so common that uses the Pythagoras sort of application. So now, recall that if I had y equals x squared, right? Really easy. When it was back in, when you first started learning the power rule for differentiation, you said dy dx equals to 2x, right? You just differentiate. That was easy. Now, the key thing to note here, and the key reason why this part of the topic is can be hard to some people, is the key thing to note is whenever you're differentiating with respect to the same variable, right, that is on the other side, there is no d whatever on this side as part of your answer. Yeah, that sort of changes when, if I want dy dt instead, right? Yeah, which is a rate. So if I wanted the rate of change of y, you actually do this by, now, the formula is driven by, basically going dy on d something over that d something on dt. You basically split this fraction into 2 parts, and you basically insert dx and dx here. Because what that means is whenever you differentiate with respect to time, dy dx, this 2x is this guy, and then you just hack on a dx dt on it. So basically you get 2x times dx dt. Now, that isn't implicit differentiation. That's just what we've been doing in rates up until now, right, for the first 2 lessons, yeah? So I guess the key thing for you to note is whenever we're differentiating with respect to no fraction, right? Or technically, for those that are really keen, technically you should have dx on dx, right? Yeah, because I'm differentiating with respect to x, and I'm differentiating a variable with x, right? But that's one, in which case you don't need to have it there at all. But basically what we're doing is, when you started learning the power rule, that was it. There's no fraction there. However, when you're doing dt, right? When you're doing dt, yeah, we must have a dx dt on the back of this to make the chain rule work. So that's super key, right? Now, what's important for you is this expression was really easy to find dy dt because y was the subject. Y was the subject. What if I gave you an expression, just like I did the last example of the last video, where it was, let's say, x squared plus y squared equals to 25. Let's choose a different number, because I think that's exactly the same as the one of the examples. Let's go equals to 100. Yep. X squared plus y. Now, there's 2 ways to do this, right? What we did in the last video was basically try to express y as a subject. So you basically bring the x squared over, square root it, right? And because x and y were lengths, we only consider positive case, right? And you basically, if you start from this formula, then dy dt, right? You basically differentiate that. You bring down the half, you minus 1 from the half, and then multiply by derivative of the inside. That's a chain rule. And then you multiply that by dx dt, right? That's exactly what we did last week. So if I'm going a bit too quickly here, refer to the last video, and that was exactly the process we did. And then if you clean this up, you get dy dx, let's see, equals to the 2's cancel out, and you get minus x on top. You bring the negative half power downstairs, so it becomes a square root. So I'm just speeding this up just to demonstrate y times dxdt. Right? That's what you got last time. Yeah. Now, there is an alternative, right? The alternative, and I love doing my alternatives in different color. So this is implicit differentiation, right? Implicit differentiation. Yeah. Whereby you don't need to make y the subject, because sometimes it's actually quite hard to make y the subject, right? I'm just going to start from this Pythagoras formula here, where if x squared plus y squared right now equals to 100. Check this out, right? What do I want at the end? Oh, sorry, I wrote that wrong. Right? So this expression here, I don't know why I put an x there. It should be a t. Right? What do I want? I want dy dt. So the question is, why do I need to make y squared or y the subject at all? Why do I need to get to this point? I can actually just apply the chain rule to each of these individual parts, the x squared and the y squared and the 100. I apply the chain rule to each one of those. I'll show you what I mean. So for the x squared, right? The chain rule basically says you differentiate it like you normally do, and then you multiply that by dxdt. For the y squared, exactly the same. Bring down the 2, differentiate it like you normally do, and then multiply that by dy dt. Constants, always differentiate to 0. Yeah, so implicit differentiation doesn't care about making a letter the subject. It just basically applies the chain rule whenever it sees a variable. It just goes differentiate it like you normally do, and then multiply it by d whatever that variable is, dt. Yeah, because then look at this, right? Let's look at this expression. I have an equation here where that side's 0, so I'm going to throw this whole thing over the fence, and I get 2x times dxdt equals to 2y, negative 2y rather, dy dt. Now, let's simplify this, right? The 2's cancel out. What am I after? Dy dt, I want to make this guy the subject, right? So then throw the negative y over the fence, and you go, therefore, dy dt equals to negative x on y times dxdt. Now, if you're thinking right now, why does this guy look different to this guy? It's not. In that, check this out. The only difference is that there's a random y variable here, right? Minus x is there, the dt is there. So then all I got to do to make it look the same is basically, for this y variable, substitute the expression for y, which is this, into there, and you get the same thing, right? You get the same thing. Get the same thing as a blue box over there. So what am I trying to demonstrate to you? I'm trying to demonstrate that you don't need to make y the subject always, right? To basically find your rate of change. You can start from the Pythagoras expression and then apply the chain rule individually. Sometimes, most times, the questions with Pythagoras are so much faster using this way. Let's try. Right? Let's try. You know what? Can I go back to the last example from last lesson where we looked at an example from Gosford that looked like this, right? You might recall this. In fact, if you don't, just go back to the video, right? Where there was an air balloon rising and there was an expression that was basically encapsulated by this diagram here, right? Now, in this question, just to really run this through, and please look at the last video if you don't remember, I'm trying to find dx dt. That is the main game, right? And I start with this expression here. So the process that Gosford led you down was it wanted you to make x a subject and go through the process of dx dt, etc. You know what? Let's do it alternatively. Alternatively, right? I'm going to start with the Pythagoras expression there, and I say to myself, well, I'm going to individually apply the chain rule there, and the 300 squared, right? So apply to the x squared, differentiate it like you normally do, and then multiply that by dx dt. For the h squared, differentiate that by with respect, like you normally do, and then multiply that by dh dt. And then the 300 squared goes away, 0, done. So that's your implicit differentiation step, right? cancel out the 2's. Now, what am I trying to do here? I'll look back at my question, dx dt. I want to make this guy the subject, right? So divide the x over. Let's see if it gives me the same answer. So then divide the x over h on x times dh on dt. And really, you're there, right? Like, because look at this. You basically go, well, h, right, just like I did over here, was 400. X was 500. And then this guy was 5, which is exactly the same as that said, right? But easier. Because then your answer is 400 and 500. That's 4 and 5 times 5 is 4 meters per second. The same answer. What do you reckon? So, if your teachers don't show you implicit differentiation, I reckon they're missing a beat, right? It is a cleaner solution for questions that don't start with the letter that you want as a subject, x squared in this case, right? And it works for any function, right? There are more complicated versions where, x squared gets a function of x gets multiplied with a function of h in this case, where you can actually use differentiation, implicit differentiation to do it much cleaner, right? Rather than trying to make x a subject, right? So, for example, like if I said to you, the formula was x squared plus 2xh plus h cubed, right, equals to 15 or something, right? In this case, to make x the subject is actually quite difficult. You have to try to complete the square and do something funky. It's insane. But if you did this by implicit differentiation, very nice, very nice. Let me get rid of that, right? Guys, once again, let me demonstrate this by bringing some questions to life. For the next ones, what I'll do it by the traditional and I'll do it by implicit, right? Just to show you both cases, right? So Norman-Hurst, now you can see Pythagoras, same concept. What to say here? Let's see, let's go through it, right? So from Norman-Hurst 2013, a ladder 5 meters long. So this ladder is at a constant 5 meters, right? So let me just write that here. So that's always 5 meters long. It's leaning against a wall and foot on the, yep. This is OB, yep. Yep, and it gives you the formula of Pythagoras, right? X squared plus y squared is 25, perfect. Before the ladder, so that's B, is starting to slide out. So this guy here is moving this way at a constant rate of 1 meter per second. That's important. Now, what does that mean? It means the distance of X is changing over time, right? In other words, this guy, 1 meter per second, represents dx dt. Yeah, because it's a change in X over time. That equals to 1. Find the speed at which the top of the ladder is moving down. So basically you want this one coming down, you want the change in y, right? So let's just highlight that in green. I always like to highlight my question in a different color. Find the speed at which the top of the ladder moving down, right? And it tells you when the top of the ladder is 4 meters above the ground. Perfect, all right? So they ask you to find speed at top of the ladder. So that is find dy dt, question mark, when the top of the ladder is 4 meters from the ground. Yeah, when y equals 4. Guys, so I got dx dt equals to 1. I got all this, right? So if you were to go traditional, right? I'll go method number 1. If you go traditional, you start with the Pythagorean equation and you try to, now what do you want dy dt? So I'm going to make y the subject, right? And y is always positive because it's a length, so get there, right? Then you differentiate that with respect to time. You go dy dt, bring down the half. So I'm just going to go quickly, bring down the half, minus 1 to the power, so it becomes negative half, multiplied by derivative of the inside, which is negative 2x. And then because I'm differentiating with respect to time, multiply that by dx dt, all right? Then a little bit of the cleanup. So then that 2 goes away, minus x is left on top. And this whole bracket thing goes downstairs because it's negative power and square root, right? So you get minus x on top, square root on the bottom, squared times dx dt. Okay. All right, what am I finding? I need to find this guy. I have this already to be 1. I don't have X, I do have Y, right? But that means, right, if I sort of think about it, at a point in time, if this is 4 meters and the ladder is always 5, then this X value would be 3, right, by Pythagoras. So in this question, it's a bit sneaky. Instead of giving you the value of X, they gave you Y, but you can work it out by Pythagoras, right? This guy are both 3s. Yeah. Then you go, this guy equals to, what's that, minus 3 on 25 minus 9 times 1. I think that's minus 3 and 4, right? Meters per second. How's that? Yeah, not bad. That's fine, right? It's fine. It's fine. This is better, right? This is better. So maybe I don't even do that. I just go step 2. Yeah. So we start with the Pythagoras. We start when we use implicit differentiation, and then I just differentiate individually, right? I want to differentiate this expression, and this expression. And I treat them individually to differentiate. So I get this guy becomes differentiate that like you normally would, but then hack on dx dt because I'm differentiating with respect to time. This guy, same deal. Bring down the 2, dy dt. This guy, constant 0. Nice. Now, and then I say to myself, okay, what do I need? What do I need to make the subject? I need to make dy this guy, right? Everything else needs to be thrown over the fence. So I'm going to throw 2x dx dt on the other side first. Yes, yes. The 2's cancel out. And then because I only want this guy, the y goes over the fence. So minus x on y. Let's see what I have here. I have an expression that looks like that. Now, in this question, I know this guy is 1. X, like I said here by Pythagoras, is 3. And y, I got it here, is 4. Easy. I know, sub it in, minus 3 on 4 times 1 meters per second. Yeah, so this method avoids sometimes silly mistakes that can occur when you differentiate square roots, right? It's not the best to differentiate square roots, but you know, choose your method, all right? Choose your poison, whichever one works for you. Please do it, right? If you're comfortable with implicit differentiation, do it. So much faster. Actually, you know what you do? So I hate to say it, there are some teachers that, I don't know, out of fear maybe, they're afraid to use that method, or they just don't know. They just didn't learn it themselves and they don't teach that method, but it's so much nicer, right? So much nicer, yeah? Let's do one more and then we'll end the video, yeah? So from the HSC 2014, right? Same deal. So there is a context, something about a radio transmitter. The car is, so it's a car traveling away, right? So car's traveling away at 100 kilometers an hour. This guy moving along the road, along this road at 100. So this is telling me that this guy is dx on dt, right? That's 100 kilometers per hour. Yeah, distance. Find an expression for x. No, in terms of x of dr. So dr dt, right? They want dr dt. Yeah, this is what I'm looking for. So let's just hop right onto the funner method, right, of implicit differentiation. So I start with Pythagoras. Yeah, 6 squared. Now, what do I want? I want dr dt, right? So I'm going to make r the subject. Yeah, so let's do that now. I'm going to differentiate each term there using implicit differentiation, where I differentiate it like I do normally, multiply by dr dt, right, equals to, differentiate that normally, dx dt, and I know that 36 goes to 0 when I differentiate. almost there. So do I know anything else? No, that's all I need, right? So what do I want? I want to make this guy the subject. So firstly, though, I will cancel out the 2's, and I'll chuck the R onto the other side. X on R times dx dt. I'm actually almost there. So the only thing I need to do now is my question. I need to sub in 100 there. Right, that's what's given in the question. Now, I don't have R. So what do I have instead? So it tells me that normally they will give you the value of X and then you can use Pythagoras, right? Normally they go, this is 6. X is like, I don't know, 8 or something, and then R is 10 or something by Pythagoras, right? In this case, slightly different, but it's actually pretty easy. They want you to find the answer in terms of X. So they'll leave X here, right? All I got to do is make R the subject and then sub it in. So in this case, come back upstairs here. I know that R equals to the square root. Now R is positive because it's the length. X squared plus 36, and then just simply plug that into there and you're done. Because everything else in there right now is in terms of X, right? So therefore, I wrote a 2 here. That should be T. Yeah, dr dt equals to X on this square root plus 36 times dx. Oh, no, times 100. So 100. Maybe I'll put it upstairs. For the X, 100x. Yeah, and that's the answer. Like 3 marks in the HSC. Did about 3-4 steps. What do you reckon? Implicit differentiation, right? Really neat method for questions where the letter isn't the subject. R squared, sometimes R cubed, don't know. That's how you do it, guys. If you like that, yeah, give me a like on the video, tell your friends, and tune in for the next video, which, yeah, I believe might be series and sequences, financial maths. Until then, catch you guys later.